Welcome to Empowered Learning. This is the third and final video in the video series on techniques of integration, where we are exploiting the use of partial fraction expansion to be able to evaluate the integral of rational functions. So in the part 1 and part 2 videos, I mainly did what's called the case 1, case 2, and case 3 types of integrals here. And so if you're not familiar with those cases, you may want to go back and watch the part 1 video, because I list them out as how they look in terms of the integrand. But here I'm going to deal with case 4, case 5, and case 6 type of integrals. So the first one I'm going to do is a case 4 type of integral. And so for this one, we know that the case 4 type of integral is such that we end up having a quadratic factor that is irreducible, and at the same time we're dealing with a case where our numerator and denominator degrees are equal to one another. Okay, so I say this is case 4, but it's really like a case 4 and a case 1, because case 1 gives us the situation here where either our degree of the numerator is actually equal to or greater than the degree of the denominator. Okay, the case 4 part comes in play because of the fact that I can take the x cubed plus 1 and I could factor that out, and even though I'm going to have factors that are prime in terms of each other, we're going to have that quadratic irreducible factor that we're going to have to deal with. Okay, so because the degree of the numerator and denominator are equal, the first thing that I must do to get this into a form to where I can even work with it is do polynomial division. And so we see here with the polynomial division, it's relatively easy. We set it up and we just say x cubed times what is x cubed, which is just 1. And then we just multiply 1 times x cubed plus 1 and then subtract. And we see that we have this remainder of minus 1. And so we know since this is a minus 1 here and not, x raised to something, we know that we can stop. And so therefore we could rewrite our integrand that we have here as just 1 minus 1 over x cubed plus 1. And so now from there, we know that x cubed plus 1 is the sum of 2 cubes, which could be factored out as you see here. And then from here, we know that for that second term in general, we have 1 divided by the product of 2 factors. So we could rewrite this second term as just the sum of basically 2 rational functions, where we use the first factor for the denominator of 1, and we use the second factor for the denominator of the other. And normally whenever we write these out, whatever the degree of the denominator is, the degree of the numerator should always be a degree lower. So here your denominator is x plus 1. X plus 1 is a polynomial of degree 1. So that means in the numerator, we have to have a polynomial of degree 0. Okay, and so literally this is like x raised to the 0 here. But of course, we know x raised to the 0 is just 1. So literally, we just have a number that's in the numerator there. Since we have our second term here that has a quadratic factor, a quadratic denominator, then that means that the degree of it is 2. Numerator must have a polynomial of degree 1. Of course, that looks like a linear expression. So now that we have that broken out here, the way that I've chosen to do this in this example is to do it the traditional way, which is I'm going to look at what I have here and kind of form it all into one quotient, and then take it from there and figure out what A, B, and C are by doing systems of equations. Okay. And so just to be clear here, what I'm noticing is that for this portion, so I'm just dealing with this part here, because I already know I can take the antiderivative of 1. That's easy, it's just x. But I need to figure out how I'm going to deal with this part. And so notice here that this 1 that's up here can be translated as 1 plus 0x plus 0x squared. Okay, and that is what I have right here. So I'm rewriting it in this way and then saying, hey, I could break it out and make it look like this. Now, of course, if I basically add these two quote-unquote fractions together, I have to have like denominators. And so I've done what I need to do to make this all into one quotient so that I have everything under one like denominator. So from there, what I am doing is I'm going to compare what I have here on the left side. So I'll circle it. So I'm comparing what I have here to what I have here. And specifically speaking, what I'm concerned with are the numerators. So whatever I have in this numerator has to equal whatever I have in this numerator here. And we know that because we know that the denominators are the same on both sides of the equation. So that is why I have 0x squared plus 0x plus 1 is equal to all of this. And of course, what I've done here from this step to here is just combine like terms to where everything in terms of x squared, everything in terms of x, and all constants were grouped together. And so from this, I know that if we look here, we know that everything that is next to x squared has to equal 0. So a plus b equals 0. We also know that 0 has to equal b plus c minus a. And we know that 1 has to equal a plus c. And so we have our system of equations here, where we have 3 equations, 3 unknowns. So we can use either substitution or elimination method to solve for a, b, and c. I chose to use substitution here. And so when I did that, I got the answers of 1/3 for a, -1/3 for b, and 2/3 for c. And so now what we know is here our value of a, our value of b, and our value of c, we now know what that is. So now what I do is I come here and say, this is what I was originally trying to work out. I know that I could rewrite it in this way where I needed to know what a, b, and c are. And so now I'm going to plug in a is 1/3, b is -1/3, and c is 2/3. And so when we do that, we see that for this portion, the minus and then all this part here, that's integrating the second term, all of that is going to look like this. And so now I'm at a point to where I know what it is that I'm going to be working with to be able to take the antiderivative of for these other two terms. And so I go ahead and work everything in. I factor out the common factor of 1/3 out of all 3 of these terms here. So that's why you see the minus 1/3 out there. And then, of course, I just have 1 over x plus 1 for the first term and 2 minus x over x squared minus x plus 1 for the second term. Okay. Now, at this point, of course, I can deal with taking the antiderivative of 1 over x plus 1 just fine. But here, I'm going to have a little problem. And so the problem that I have there is that at first glance, I would want to use substitution rule. Okay. So if I did that, then I would say, hey, let's let u equal x squared minus x plus 1. Okay. Because that's more than likely what we would have to use in order to make this work. But of course, du in this case would be 2x minus 1 dx. And the problem that I have here is that I don't have a 2x minus 1 dx here, or anything that looks remotely close to it. So I'm in a situation where I have some problems, okay? Now, of course, I could, do something fancy like factor out a 2 and say, all right, well, let's let du over 2 equal x minus 1/2 dx. I could do that, okay? But still, even in doing that, that means that I would have to figure out now, well, how does this x minus 1/2, how does that equate to this? And then, I'm going to have some baggage that's kind of left over from that. And I'm essentially going to have to break out and do another term anyway, okay? So it's really not helping me much to kind of take the traditional substitution route to solve this. Now, one of the things that we can do here, and this is what I note with what I'm trying to say here, is that we could work on this irreducible quadratic factor in the denominator and perform completing the square on it, okay? If we did that, then using this u substitution here to get this x minus 1/2 dx, that would actually make a little bit more sense now, because what we're going to see is that we are going to have a term that's going to have x minus 1/2 in it, okay? So we do the completing the square method here, and essentially we're just, of course, going to introduce a term there and subtract it out, and we just take whatever number this is, which is a minus 1 in this case, divided by 2 and square it in the blanks. And then, of course, we factor, and what we see is that the x squared minus x plus 1 can be written as x minus 1/2 squared plus square root of 3 over 2 quantity squared equivalent, okay? So now that we know that, we replace the x squared minus x plus 1 in the denominator with the vertex form of this, and then we commence to go and trying to rewrite all of this, okay? So we see now that we have this case where we have this x minus 1/2 squared in it. So we're going to try to massage what this looks like to have that x minus 1/2 show up somewhere. And so we can do that by looking at our numerator and realizing that 2 is just the same as 1/2 plus 3/2. So negative 2 is going to be the same as a minus 1/2 minus 3/2. And so if we split it up that way, we see that we get what we want here. But again, the whole sacrifice of all of this is that we still end up having to break this out into an extra term, okay? And so what I've done here is out of both of these terms in the numerator, I went ahead and I factored out a negative 1/2 out of all terms. And so that's how I get the 2x here, minus 1, and minus 3 there. And again, I'm doing that because in the long run, it's going to make evaluating what I need to evaluate for these integrals easy, okay? So if I keep on going here, then I go back to what gamma originally was, okay, which is, this is what it looked like. And so now I'm saying that now I'm going to rewrite it in this way, where I have the 1/2 out, I have the 2x minus 1 over this denominator, minus 3 over this same denominator. So I'm just breaking it out here, okay? And so then from there, all that I'm doing at this point is realizing for this first term that all of this is just x squared minus x plus 1. And so now that I have it looking like what I want, if I was to use the substitution rule on it here, it would actually work out fine. But again, the price that I'm paying for that is the fact that I have this extra term that I had to break out. So I originally had when I was looking at this, I originally had just one term to deal with, but now I have two to deal with. Okay. And so now that's why I labeled these A and B to show you how I deal with these separately. So evaluating the A integral, we're just going to use substitution rule. That one's relatively easy. So if we let u equal the quadratic expression in the denominator, and of course if we take the derivative of that, we have du is equal to 2x minus 1, all that times dx. So with that, we see here that this 2x minus 1 dx is just going to be du. And of course, x squared minus x plus 1 is just u. We take the antiderivative, and that's just going to be natural log of absolute value of u. And of course, we got that constant of negative 1/2 on the outside here. And I've labeled this integration constant c sub a just because it is the integration constant that comes from evaluating the integral a. And that's my way of trying to keep up with all the stuff that we're going to have to do here. So we see that for this situation here, our integral a just ends up being a negative 1/2 natural log of the quadratic factor that we ended up with. So for integral b, we notice here that this has a look something like 1 over w squared plus a squared. So it looks something like that. Okay. So here, what I choose to do is go ahead and do substitution here, just to make it look a little bit more simple. Okay. And then at this point, the approach that I took, not necessarily the approach I needed to take here, but it was just one that I thought of at the time, is I used trigonometric substitution here. Okay. And so I'll show you how this works with trigonometric substitution, but there is a faster way to do this by just knowing what the antiderivative of this is going to be in terms of arctangent, because that's what it's going to turn out to be. Okay. But if you didn't know that, of course, you could do this trigonometric substitution and figure it out. So I'll show you the trig substitution first, and then I'll show you how we can just do this simply just by knowing the antiderivative of arctangent. So here, if I use that w is equal to square root of 3 over 2 tangent of theta, and I'm doing that because, again, if we look at this, this looks very similar to tangent squared theta plus 1. Okay. And if I was to make this 1a squared, then I would have to have a squared here. And this would just be a times tangent theta squared plus a squared. Okay. And so that kind of fits that particular trig identity. So we would have to take whatever, the square root of 3 over 2 part here and multiply that, and let that be our a here, and multiply it times tangent. Okay. So from there, of course, once we know what the substitution is, we take the derivative of w with respect to theta. We see what that ends up being, and then we just substitute everything in. Okay. And once you do that and a whole bunch of simplification, we just get to this particular point here. And of course, theta, if we think about it here, we could solve for theta just using this particular equation there. Okay. So if we were to solve for it, it would actually just be 2w divided by square root of 3. And that would equal to, tangent theta. And then, of course, if we did tangent inverse of that, that would actually just end up being what theta is. So that's how we would rewrite theta in terms of w. And of course, w was just x raised to the 1/2. So we can replace that w that we have there with x minus 1/2. Okay. So here, this is just me kind of going through all this to finally get to that answer. And so you see that this is what this is here. Okay. Now, Again, I mentioned that the integral that we had whenever we were at this point, this integral here is actually of this particular form. So we could have just went directly and just used this formula here to come up with the same thing. Okay, and so that is what I was alluding to. Okay, you got several ways you can do this. At the time I worked it, for whatever reason, I just felt like doing a trigonometric substitution. Okay. All right. So anyway, so now that we know what all this ends up being as a result, we know that, and let me go back here. So we were at a point, I'm going to go back all the way here, where we had got to a point in our problem to where we were like, hey, I can pretty much figure out everything else except for what this gamma is. And so the last page or so has been us working on to figure out what this gamma portion of this minus integral of g of x is going to be. Okay. So in other words, we've been dealing with this, and when we broke this out and we said, hey, we got to break this out into two terms, we know that this second term here, which is actually the third term, we had to work on that and massage it a bit. And so that is what all this business was about. Okay. And so now we're just kind of putting everything together and wrapping it up. So now that we have all of our answers for all the integrals that we really needed to deal with here, so we just once and for all state what minus the integral of g of x is, which is basically what we were dealing with. And so we do all that, have this, have that, have that. So we got the three terms, and we got the answers for each of them. And then, of course, the integral of what we were beginning with is just going to be all three of these terms again together. But now we actually have to add it to x plus c prime. And that comes from way back here in the beginning, where we had this 1 that popped out, and we know that the antiderivative of 1 is just going to be x. Okay, so when we got to the point of just saying, hey, well, what is antiderivative of 1? Remember, we just said it's going to be x plus c prime. Okay, and I think I named this 2 pages later x plus c sub 0. So that's where all that comes from. Yeah, so, okay, I still named it c prime, so that's good. All right, so this comes from the first part that we know. This was all the stuff that we were working on for the past 2 pages. And again, we just put it all together and say that, hey, our final answer is just going to be all this business here, where our constant c is just all these little integration constants kind of wrapped up together. Okay. And so, yes, this problem is involved. Yes, it has a lot going on with it. But yes, these are the types of integrals that we actually use this technique for. Okay. All right. So let's look at a case 5 situation. So the key thing in a case 4 situation is that we have a quadratic factor that's irreducible that we're dealing with. For a case 5 situation, what's special about it is that not only do we have a quadratic factor that's irreducible, but we have it repeating in our denominator. Okay, and so this is what this case 5 example is going to show. How do we deal with that? Okay, and so the first thing here is that we notice that the degree of the numerator, which is 3, is less than the degree of the denominator. So we have a quadratic factor that's squared, so that's going to make that polynomial in the denominator have a degree of 4. So because we do that, we do the best that we can to try to factor out what's going on in our numerator and denominator. Unfortunately, there's not too much we could do here to factor out the denominator in a meaningful way. But what this is showing you here is that how we actually deal with repeating factors. Okay, so for instance, if I wanted to add, let's say, 1/3 plus 2/9, I know that the result of that, if once I get the common denominator of 9 here, I would multiply numerator and denominator by 3, and this would be 3/9 plus 2/9, which will be 5/9. Okay. Now, this strategy of taking this particular rational expression here, or this rational function, and we're going to split it out into two terms where one of the denominators for the term is going to be quadratic like this, and the other one is just going to be that same quadratic denominator but squared. Its motivation comes from the same thing that we're doing here with this simple process of adding two fractions. Okay, so right now this rational function is kind of like having 5/9, and what we want to do is break down 5/9 to look like this. Now, the reason why this makes sense is because if you think about it, 9 is the same thing as 3 squared. Okay, so essentially we have 1/3 plus 2 times 3 squared, just like we have something divided by a quadratic factor plus something divided by a quadratic factor squared. Okay, and so we know that because of the fact that our result here is a denominator that is that something that we're dealing with squared, we know that we could break it out this way. And because of the fact that this quadratic factor, that this denominator is quadratic, that means our numerator is going to have to be 1 degree lower. And of course, the way that this works whenever we have the repeating factors is that we also make the numerator of the one where the denominator is squared also be linear. Okay, and so from here, since we don't have any linear denominator factors, we can't use the shortcut method. So we're doing this the traditional way by just saying, well, hey, what is all this stuff here going to look like if we combine it into one quotient, okay, with the A's, B's, and C's in it. And so we see that this is what it ends up looking like. And so now what's important to us is that our numerator on the right hand side equals our numerator on the left hand side. So that is what this step is all about here. And then of course from there we just need to multiply everything and combine like terms so that we'll know everything that is in terms of x cubed, everything that is in terms of x squared, everything that is in terms of x, and everything that are just constants. And so we see that once all that's done here, then of course a is going to go with the 1 here, 2a plus b is going to go with the 2 here, 2a plus 2b plus c is going to go with the 3 here, and 2b plus d is going to go with the -2 there. And so when we essentially categorize everything, this is what we get. And because of the fact that we know that a is 1, we can just plug a into here to figure out what b is. Plug in both a and b into here to figure out what c is. And then after that, we can plug in what we know for b to figure out what d is. Okay, and we see that b ends up being 0, c ends up being 1, d ends up being a -2. And of course, a, of course, we had already found that was 1. So what we're doing here now is we're going to take what this particular version of our rational function now looks like, and we're going to substitute in what a, b, C, and D are, and then deal with taking the antiderivative of those terms from there. Okay. So again, my point is we've done all that so that we could actually know what are those real numbers A, B, C, and D, so that we can start to try to take the antiderivative of these two terms. So we go ahead and we fill everything in. So here, remember, this was AX plus B in the numerator. This was CX plus D in the numerator. And if you remember here, our A was 1, so that's why we have understood 1 here. Our B was 0, so that's why you see nothing here. Our C was 1, so that's why we have understood 1 there. And of course, our D was minus 2, so that's why you see the minus 2 there. So once all that's done here, we notice that our denominator here, we could rewrite this using completing the square as just x squared plus 1 quantity squared plus 1. And that works out well for us to write it that way, because it makes it also easier for us to rewrite our numerator in this first term, because we know that x is the same as just x plus 1 minus 1. So that's what we've written here. And of course, we see that they have the x plus 1 terms in the numerator and denominator. So that lets us know that we can do some form of substitution here. Okay. Now, with second term, we could break out. We can break this out. But before we do that, again, we notice that our denominator here is just going to be the same thing that we had in this first term, but it's just squared. So we need to rewrite this in a way to where we can have the x plus 1 showing up there too. And so to get that to equivalently be there, we know that 2 is the same as 1 minus 3. So we just say plus 1 minus 3. We have the x plus 1 here, and that's going to match what we have going on there. So we know that there's going to be some form of substitution that we can do. But again, the price that we're going to have to pay is we're going to have to split out this one term here into two terms as well. So you see that we end up having 4 different integrals that we are antiderivatives that we're going to have to do. So for this first one, F1, this is just going to be simple substitution. Same deal here. This is going to be simple substitution. For these two, we're going to have to, they're going to be some form of tangent inverse, but we're going to have to massage some of them to make it look like what we want, since we have this x plus 1 in here. But essentially, again, both f sub 2 and f sub 4, the antiderivatives are going to be some variation of tangent inverse. So to solve for the integral where the integrand is f sub 1, notice here that if we let u be just our quadratic factor here, if we take the derivative of it, and that's just going to be 2x plus 2, which if we factor out the 2, gives us the 2 times x plus 1. And it's really the x plus 1 dx part that we're looking for. So we need to be able to replace this in terms of u. And so now we have that. So now we can take this x plus 1 dx and just replace it with 1/2 du. And take our quadratic factor in the denominator, replace that with u, and then just take the antiderivative. And of course, everything is kind of easy from there. Okay. So the antiderivative of du over u is just natural log of absolute value of u. Plug back in, u was that quadratic factor. And then here, I've just said that 1/2 times natural log of anything is just natural log of square root of that anything. Okay, and so that is what your function f1 of x is going to look like. Okay. So now for sub 2, we do substitution here. X plus 1, let that be w. And so luckily for us, we know that dw is just going to be equal to dx. And we also note that 1 divided by x squared plus a squared, where a is a constant, that antiderivative is just 1 over a times arctangent of x divided by a. So in this case, we see that if we have this minus 1 over x squared plus 1 squared plus 1 squared, all in the denominator, then this just translates directly into the antiderivative, where it's tangent inverse. And so then we just clean it up and make it look nice, and thus minus tangent inverse of x plus 1 plus the second integration constant is what f2 is. Okay. So moving forward here, we have f sub 3. Same kind of situation that we had before with the substitution with f sub 1. We just let our quadratic factor here be the substitution. Of course, same kind of thing. If u is x squared plus 2x plus 2, then that means that 1/2 du is going to be x plus 1 times dx. So you see all of this gets replaced with 1/2 du, and again the x squared plus 2x plus 2 ends up just getting replaced with u. And so now we just have to take the antiderivative of 1/2 times u raised to the negative 2, which we see that's just going to be a negative 1/2 times 1 over u. And then, of course, we can just plug in what u was, which was our quadratic expression. And again, we got our integration constant. So lastly, with number 4. So for this one, we see that we have something that looks kind of close to something that would give us tangent inverse here. But notice that we got the squared there, okay? And I believe, I don't know if I wrote that or not whenever we were back here. Oh yeah, I have it here, but I didn't see this. So because of the fact that we have a squared there, we're not going to be able to do the whole tangent inverse thing like I had originally said here, okay? So we know this one is going to be some rendition of tangent inverse, but of course this one is going to be something totally different. So we're going to have to deal with it. So I'm going to go jump back there and then see how we're actually going to have to deal with that. So because of the fact that we have this x plus 1 squared plus 1 and all that squared, we're not going to be able to simply just use tangent inverse as the antiderivative and kind of get out of this. So at this point I'm using trigonometric substitution, since again what we're seeing here kind of mimics this whole thing of tangent squared of theta plus 1. Okay, so it kind of looks something like this. And I know that tangent squared theta plus 1 is just secant squared theta. And so to make life simple for myself, I say, hey, this substitution here is just going to be equal to tangent theta. And we're going to see how it comes out if things are expressed trigonometrically and instead of algebraically. So we see that if x plus 1 is equal to tangent theta, then of course x is going to be tangent theta minus 1. And if we take the derivative of what we got going on here, this is just going to be secant squared theta d theta. And so we need to know all that business because of the fact that, of course, we want to replace dx here. Okay. I also need to know what x plus 1 is. Okay. So now I go and actually fill in all that information. So x plus 1 just ends up being tangent theta. So we see here x plus 1 squared is tangent squared. We see dx is secant squared theta d theta. So we see that we fill in all that information. And then, of course, tangent squared theta plus 1 is secant squared theta. But remember, all that is squared. So that's actually secant to the 4th. And so now from here, secant squared over secant to the 4th is just going to be 1 over secant squared. And of course, the reciprocal of secant is cosine, because that's what this actually is, the reciprocal of secant squared. So that's going to be cosine squared. And with us having cosine squared, we now need to know our reduction formula, trig identities, to be able to write that into a form to where we can actually take the antiderivative of it. So we know that cosine squared of theta is just going to be 1/2 of cosine of 2 theta plus 1. So this is a trig identity here. And this is good because we can take the antiderivative of 2 theta with ease. We can take the derivative of 1 with ease. Okay, so the antiderivative of cosine of 2 theta is just going to be sine of 2 theta divided by 2. And the antiderivative of 1 with respect to theta is just going to be theta. And so we now have what our answer is going to be, which is negative 3/4 sine of 2 theta minus 3/2 theta plus this integration constant. All that is in terms of theta. Okay, but what we need is everything in terms of x. So therefore, I'm going to have to rewrite what I have here in terms of theta to be in terms of x. And so you can see how this gets real interesting. So I use the fact that sine of 2 theta is just going to be 2 times sine theta cosine theta. And I reduce what I have up here. Of course, I have a common factor of 2 here and here that I can reduce to 1. And then what I end up having left here is just negative 3 over 2. So both terms have a negative 3 over 2 in it, so I factor that out. And then now from here, I see that I have sine theta times cosine theta, all that plus theta. Okay, and if we remember here that our tangent theta was equal to x plus 1, then if we use our whole trigonometric substitution thing here that we do whenever we deal with those types of integrals, to say, hey, we can do this whole right triangle thing and see what is the relationship of sine and cosine and secant and cotangent, all in terms of theta based upon this definition here. So tangent, of course, is opposite over adjacent. So, of course, if we square 1 and then square x plus 1 and then take the square root of that, we just end up getting square root of x squared plus 2x plus 2. And so from there, now that we know what all 3 sides of our right triangle looks like, we can now read our triangle and figure out what is sine and what is cosine in terms of x. So, of course, sine is going to be opposite over hypotenuse. And, of course, cosine is going to be adjacent over hypotenuse. So that's how we get these 2 answers here. And as I mentioned earlier, that theta here is just going to be tangent inverse of x minus 1. So that's what you see here. So now, this last one, so all this is for this f of force of x here for this particular integrand. All of that ends up being all these 2 terms here. Okay, so we had to really work for that last one. Okay, so once we have that, then we just put everything together here. So we just take the antiderivative of all 4 of these, which we've already found. So, and we see that that just ends up being all of this business here. And of course, from this point, the only thing that I'm doing up from here down to the end is just trying to make it look a little bit nicer. But at this point, this is at a minimum how far you need to go. All right, so for our very last example here, this is a case 6 example. And so our case 6 types of integrals that we deal with are the ones that end up actually having radical expressions in the terms. And so part of the reason why this is a part of partial fraction expansion is because our goal here is to take these radical expressions that we have and do substitution on them so that we turn our integrand from looking like fractions where they got terms with radical expressions in them to something that looks like a polynomial in the numerator and denominator. AKA, we want to change what we're looking at in the integrand to something that looks like a rational function. And of course, once we do that, we can employ either cases 1 through 5, depending upon what we get, to be able to get our final answer for this particular interval. So we start off here by noticing, hey, I got square roots and I got cube roots, okay? And the one thing that we need to remember here, just in general, if I have 2 and I have 3, the least common denominator in between 2 and 3, or the least common multiple in between 2 and 3 is 6, because we know 2 times 3 is 6. Now, the reason that's important is because x, square root of x is just x raised to the 1/2. And cube root of x is just x raised to the 1/3. If I wanted to multiply these two expressions together here, I wouldn't be able to really use my exponential rules like talking about unless I had this situation here. Okay, so I could do that, but to be able to get this 1/2 plus 1/3 into one single number here, of course, I would have to find equivalent fractions and add these together. And of course, when I do that, I'll end up getting 5/6 here when I do it. So my point here is that we could take what we have here and rewrite this in terms of something raised to a fraction where its denominator is going to be 6, and same deal here. We could rewrite it that way. And so that is what I'm trying to illuminate here. That I want to express square root of x as a 6th root of something. And I know that expressing as a 6th root of something would be the 6th root of x cubed. Okay? And of course, I could express it this way. Now, I want to express the cube root of something as the 6th root of something as well. Okay? And of course, in this case, the cube root of something is just going to be the 6th root of x squared. Okay? So now that we have all that, then the one thing that is in common in both of these, whether we have x raised to the 3/6 or x raised to the 2/6, all of them have x raised to the 1/6 in it. And so I can look at this x cubed here as x raised to the 1/6, all of that squared. And I can look at square root of x as x raised to the 1/6, all that cubed. So if I let the 6th root of x, or x raised to the 1/6, actually be u, then what turns out here is that this expression that I have in my integrand will actually end up looking like a rational function. And of course, if I do the substitution of u, I have to find out what the derivative of u is with respect to x. Of course, it ends up being that. And you see how we're just trying to rewrite it in such a way to where this x raised to the 1/6 just ends up being u. So now pretty much everything could be expressed in terms of u. Okay. And so in this next step here, we got all this business here. We're just trying to make this, of course, again, look a little different. So we know that once we're done here, if we solve for dx, then dx is just going to be 6 divided by u raised to the negative 5, or put another way, it's just going to be 6 times u raised to the positive 5 du. Okay, so we do all that heavy lifting to get to this point. So now dx is the same thing as all this, and our square root of x in terms of u, let's try to see, where am I at here? Yeah. So here, this is what my square root of x is in terms of u, and I know that x raised to the 1/6 is going to be u, so that's just u cubed. Okay. Now I also see that my cube root of x, when I express it, it looks like this, and that x raised to the 1/6 is just u, so I could look at this as u squared. So I replace square root of x with u cubed, cube root of x with u squared. And of course I have the 6 times u raised to the 5 on top here. So now I have a situation where I have a rational function in my integrand. I know that both of these terms have a common factor of u squared, so I'll go ahead and factor that out. And then of course u to the 5 divided by u squared, that's just going to be u cubed, and that's what I see here. And so now at this point, this looks like a case 1 type situation where we will just do polynomial division here. And you see that I'm doing that here so that this u cubed divided by u minus 1, all that could just be rewritten this way. And of course, once we have that, I can integrate all 3 of those terms relatively easy, and I can integrate that last term. So the hard part was to get it looking like how we have it now. And so now all we do is just integrate all 4 of these terms and take the antiderivative of each term. And then after we're done with that, of course, we'll take the 6, multiply it through to make it look a little bit nicer. Next step is we remember here that u was indeed x raised to the 1/6, or the 6th root of x. So you substitute that back in. We use our exponential rules here to simplify what we can. So that's how we get the square root of x here, cube root of x there. And then from that point, that is pretty much it. So our last step here is just translating everything back into its radical form, because our problem was originally given to us in radical form. Okay? And so again, I know these examples are a bit involved, but I do need to expose you to at least some that look like this, so that you kind of know, hey, once you start dealing with problems that are a little bit more complex, you at least have an idea of how to deal. Okay. All right, so this is the last example of this video and the last example of this series of videos on techniques of integration, where we exploit the partial fraction expansion technique to evaluate the integrals of rational functions. I hope these videos help to shed some light on how to approach these types of problems, and I'll see you in the next video. Take care.